This lesson is about conservation of mechanical energy, and here are your objectives. First, let's define total mechanical energy. We'll define it as the sum of an object's kinetic energy, gravitational potential energy, and spring potential energy. Now, if forces external to the system, meaning forces other than the force of gravity or the elastic force of a spring, do work on an object, then they're going to change its total mechanical energy. Now, you might ask, well, what about the force of gravity and the elastic force? Well, by introducing these potential energy terms, we have implied that the Earth and the spring are part of our system, and therefore the forces that they exert are internal forces. And so those forces are not going to change the total mechanical energy of our object. Let's take a look at a couple of examples. Here we have a 200 Newton force acting on a box that's initially at rest and pushing it through a displacement of 3 meters. Let's draw bar graphs of the different energy and work over here. So if it's initially at rest, its kinetic energy is 0. And if I make the reference height the ground that it's on, then its gravitational potential energy is also 0. And because it's not going up or down, its final gravitational potential energy is 0 as well. Now, if I exert a force of 200 newtons through 3 meters, that's a 600 joule work. That's 600 joules of work that I've done on the object. Now again, gravitational potential energy doesn't increase, so if this is a frictionless surface, that work is going to become the kinetic energy of the object. So the box is going to have 600 joules of kinetic energy, and if we knew the mass, because kinetic energy is equal to 1/2 mv squared, we could then find its speed. Now, what if it wasn't a frictionless surface and there was friction between the box and the ground or the table that it's on? Well, then some or even all of this work could be transformed into internal energy, not kinetic energy. Internal energy being the energy that's reflecting the way that the box and the ground warm up. Let's do another example. Here we have a box that's lifted through 1.5 meters. Its weight is 100 newtons, and so in order to counteract that and move that at constant speed, we need to exert an equal and opposite upwards force. So we're applying a 100 newtons upwards force, while there's also its 100 newtons weight downwards. Its initial kinetic energy in this case is not 0. It's given to us as being 50 joules. So we have a 50 joule initial kinetic energy. Now, if we set our reference height at the bottom position, then its initial gravitational potential energy is 0. If we exert a 100 Newton force through 1.5 meters, that's 150 joules of work that we're doing. So we have an external work of 150 joules. Now, we're told that the speed is constant, and therefore the kinetic energy is also constant, so we have a 50 joule kinetic energy at the end of the problem. Well, where does the 150 joules of work go? It goes into raising its gravitational potential energy. So the gravitational potential energy at the end is 150 joules. So positive external work increases kinetic energy, potential energy, or both. And negative external work would do the opposite. It decreases kinetic energy, potential energy, or both. The initial energy of the system plus the external work that we put into the system therefore gives us the final energy of the system, as we've seen up here in these examples. This brings us to the principal conservation of energy. In the special case where there is no external work, where this term becomes 0, then the initial energy of the system and the final energy of the system are the same. In other words, when there are no external forces, no forces other than gravity or the elastic force doing work on the system, then the total mechanical energy of a system remains constant. The initial kinetic energy, the initial gravitational potential energy, and the initial spring energy are equal to the final kinetic energy, the final gravitational potential energy, and the final spring energy. Those two sums are equal to each other. Let's take a look at an example. We've got a roller coaster at rest at the top of a hill of height 50 meters, and we're asked to find the speed at the bottom and told that we can ignore air resistance and friction between the track and the coaster. Let's think about the forms that energy takes in this problem. At the start of the problem, the object is at rest, the coaster is at rest, and it only has gravitational potential energy. Whereas at the end, if we set the reference height to where the coaster ends up at the end of the problem, then at the end of the problem, it only has kinetic energy. And there are no forces other than the force of gravity that are doing work on the coaster. And therefore, the initial energy is equal to the final energy. Or mgh, remember that our formula for gravitational potential energy is that the change in potential energy in raising the coaster up from the height of 0 is equal to mg delta h. And so therefore, we have mgh as its potential energy at this spot. That potential energy is equal to the kinetic energy at the end, because its energy is only gravitational potential energy at the start and only kinetic at the end. Notice here that mass actually cancels, and so we can rearrange for the speed, which gives us 2gh. Sorry, the square root of 2gh. If we plug in then 2 times 9.81 meters per second squared times our height of 50 meters and solve, we get 31.3-ish, or to two significant figures, I'm going to imagine that that's two significant figures, 31 meters per second. Now you might ask, what about the normal force? The normal force is acting on the coaster, and that's not either gravity or the spring force, it's external. But the normal force always acts perpendicular to the direction of motion. At any moment, the coaster is moving along the track, and the normal force is pointing perpendicular to that, and therefore it does no work. So that's an introduction to the principle of conservation of energy.